Like maybe the first 2 hours, and then after that, I'll be like,
Okay. So now we're into the chapter which is called applications of derivatives. Applications is a fancy name for word problems. I know usually no one likes word problems in math. These I think are actually not bad word problems. Hopefully once you see the pattern, it will make complete sense to you. Because they just all tend to be the same exact thing over and over again. Let me explain real quick what related rates is and means, though. Just take a few quick notes for me. If you want to do it on the back of that, if you want to do it in your notebook, that's fine with me. So they are problems involving variables. Yeah, you can do it there if you want to. It's fine with me. Changing with respect to time. And that's the key right there. We're no longer working with problems that are changing with respect to x. That's what we've been doing the whole entire time. We always take a derivative. It would already be solved for y, and we'd be taking a derivative with respect to what's called x. Now we're respecting time. So if that doesn't make sense to you, it's okay. It will in a minute. Here's the big clue. If it doesn't have a t, if it doesn't have the variable t, then you must include d, whatever the variable is, t, dt. If it doesn't have a t, you must include d, whatever the variable is, dt, meaning this, we're going to do an implicit differentiation. Remember when we were taking implicit differentiation, if it was a y, we would write dy dx after we took the derivative. If it was an r, we'd write dr dx, whatever it had. This time we're respecting time, so everything is going to be in terms of time. If you don't see a t, then you have to write d, whatever the variable is, over dt next to it. That's the big hint. So we're going to do one quick example that's not really a word problem. And it'll kind of lead into what we're doing today. Find dy dt given x equals 3 and y equals x squared plus 3 if dx dt equals 2. So this is not really a word problem. It's really understanding notation and what they're giving you here. So don't freak out. But here's what they're always going to do. They're always going to give you some kind of formula. Or actually, I take that back. You're going to find the formula. You will already know these formulas. They're mostly geometric formulas from geometry. So they should all be familiar to you. In this case, this is the formula they've given to us. So we're going to start there. And you are going to do an implicit differentiation on it. Okay. So if I asked you, what would the derivative of y be? You would all tell me what? You would normally go dy dx, right? But if we're respecting time, we would say dy dt. So everything has to be in respect to time. What's the derivative of x squared? 2x, but did I take a derivative of a t? So I have to include dx dt. Everything gets a d, whatever the variable is, over dt, unless it has a t. What's the derivative of 3? 0. Okay. So once we take the implicit differentiation, we do everything with respect to time. We attach everything with a respect to time. I now plug in the rest of the information. So this says find dy dt. So that's what I'm going to find. This line here means given x equals 3. So right here at this x, I'm going to put a 3. And what else do I know? And given this formula, if dx dt equals 2. So right here at dx dt, what am I going to put? 2. So what is my answer? 12. Okay. So again, well, this means nothing to me. I know. We're going to put a story to it in a minute. I just wanted you to do one without words. So it just like, this is really all you're doing. You're going to get a formula. You're going to take an implicit differentiation of it, and then you're going to have to plug in things and answer the problem, okay? One last thing before we actually do the word problems. So these are words that mean derivative, or words for the word derivative. You know, when you were first learning word problems and your teacher would give you words for addition, sum, words for division, quotient, right? These are words that mean derivative. So when you see this phrase, I guess I should say, rate of change, that means derivative. When you see increasing or even decreasing at a rate of, there's that word rate again. Remember, rate is just slope. When you see change in, the change in the diameter, the change in the volume, okay? That is another word for derivative. Even something like how fast is the rate? They like that rate word, by the way. Those all mean derivative. Those all mean derivative. Okay, when you're done with that, take out that little sheet that I gave you, and you can see I've titled this, related rates 2.8. It's really 4.1. Pebbles, balloons, conical shapes, and ladders. Because, not lying to you, everybody who teaches this does the same exact ones over and over again. A pebble, a balloon, a ladder. It's always the same thing. Math teachers are so predictable. So even in your next SBCC test, this is all over it, and you might as well just keep this for notes. It's super fun. All right, so we're going to do this first one together, and after I've been teaching this for a very long time, probably about 2 years ago is when I finally decided to change. I really should have changed these boxes around because then the kids were understanding it when I changed boxes around, but it's still going to be helpful so you see what I mean. So let's read the sentence, this word problem first. A pebble, a good old pebble, is dropped into a calm pool causing concentric circles. The radius r of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4, what rate is the total area changing? Did you hear those words, rate, coming in? Changing, okay? All right. First thing is you really should draw a diagram because we are talking about a circle, and in circles, we only need to know the radius. You should remember that from back in the geometric days, okay? Now, I would say skip the second one. I used to make the children do this, but they didn't understand it. So I'm actually going to go to number 2, the equation part, because you should all know the equation for a circle. What's the equation for a circle? Pi r squared. By the way, we're not talking about circumference, right? We're talking about the area, the outer ripple expanding the area of it. So area, please write the A, equals pi r squared. Now we're going to go over here to 3, the derivative. We're actually going to take the derivative implicitly of this formula. What's the derivative of A then? What would I write? dA dt. What's the derivative of pi r squared? Remember, pi is a number like 3r squared. What would you do if it was 3r squared? What would you do? 2 times pi r to the 1, and then what would you need to include? dr dt. These are all rates. So real quick before I move on, let me explain what this is. This is a derivative or a rate of what? Rate of, what is A? The area changing. What is this derivative of? The rate of the radius changing. So let's see if we can go back in the story and find these things out. A pebble is dropped into a calm pool causing concentric circles. The radius r of the outer ripple is increasing at a rate. What is that?
Slope.
Of what?
Radius.
So this is dr dt. The rate at which the radius is changing is 1 foot per second. When the radius is 4, what would that be in my story? R equals 4. what is the rate the total area is changing? So that is my dA dt. That's what I need to figure out. So now I take these and I plug them into here. So this would be stay 2, this would stay pi. My r, this moment in time when the outer ripple is 4 feet, so I'm going to put a 4 right here. What's my dr dt? 1. 2 times pi times 4 is actually, you can leave it in terms of pi. That's how I actually like it. 8 pi. And we're talking about area, so we would end it with feet squared per second. That is the rate at which the pebble is changing the area. Now, again, like you're like, who cares about this? Let me tell you where it cares, okay? I don't know if you know this, but years ago, there would be like oil tankers that would spill into the Atlantic Ocean. And there are scientists that have to figure out how quickly that area is changing. Pretty much how quickly is it getting to the shore? And so they have to figure it out. That's where this stuff comes into play. That's where calculus comes into play. That was what we call the easy one. We're going to work our way to the harder ones. Next page. Okay, air is being pumped into a spherical balloon at a rate, there's that phrase again, of 4.5 inches cubed per minute. Find the rate of change of the radius when the radius is 2. Okay, so just drawing myself a picture, you have a spherical balloon and you have air that's being pumped into it. So you need an R. For those who don't remember, I'll give you the equation. By the way, we're talking about surface area of the sphere or volume when you're pumping in air. What would be changing? Volume. So we're going to find volume of the sphere is equivalent, for those who don't remember geometry, 4/3 pi r cubed. That's why geometry is important. Okay? Now. Now, what would be the derivative of this? What's the derivative of v? dv dt. What's the derivative of 4/3 pi r to the third? Multiply those together, yes. 4 pi r what? Squared. And what do I attach? dr dt. Okay, so if you notice, I need 3 unknowns right here. dv dt is unknown, r is unknown, and dr dt. So those I'm going to go back into my story and figure out which one is which. Okay? So air is being pumped into the spherical balloon at a rate of 4.5 inches cubed per minute. What would that be? What's changing here if it's a rate? The radius? If air is being pumped, the dv dt. Here's another clue. Do you see how it says, I know it has a 3 next to it, inches cubed? What do we always label as cubed? Volume. So this is dv dt. Air is being pumped at 4.5 inches cubed per minute. Find the rate of change of the radius. What's that? dr dt. That's what I got to find. When the radius is 2, that's my r. Okay? We're going to take those and plug them into our formula down here at number 3. So dv dt, they actually told us what that is. It's 4.5. 4 pi, leave the same. R is 2, but square it. And dr dt is what I need to figure out. So this becomes 4 squared, 16 pi. So I'm going to divide by 16 pi. I do want you to take out your calculator. Here's why. Many students will punch this into their calculator wrong. If you put 4.5 divided by 16 and then pi, you're wrong. You have to put a big old parenthesis around the entire bottom 16 pi to get the correct answer. And I don't have my, is she coming? Freaking me out. Gray, what'd you get? 0.0 something.
0.089.
Okay, so 0.09, that's what I have.
Yes.
Inches. So the rate at which the radius is changing at that moment in time, you're blowing up this this spherical balloon, when the radius is 2 inches, it's changing at a rate. It's going that fast as 0.09 inches per minute. Okay. And again, you're like, who cares? But there are things that people care for. This is one of them. All right. Next one is probably the hardest one, the ladder problems. Okay. Because ladders, you got to do an extra step for. So yeah, can you think of ladders in your past geometry skills and what formula always came up with ladders leaning against walls? What kind of Pythagorean theorem? Okay. So a 41-foot ladder is leaning against a wall and the top is sliding down the wall while the bottom of it slides away from the wall at 4 feet per second. How fast is the top sliding when it's 9 feet above the ground? So let's draw this out to give ourselves a picture. Here's the wall. Here's good old ladder. And there's the bottom, okay? Now you are gonna put in some information. 41 is the ladder, which is also your hypotenuse, right? That's your C. Do you know A and B? No, so we're gonna just put A and B right now. Even though it says how fast is the top sliding when it's 9 feet above the ground, that's for the second picture, so hold on, draw this part first. Go over here to number 2, the equation. Your equation for a right triangle is a squared plus b squared equals, which in this case is 41 squared. Or a squared plus b squared is actually 1681. I'll give that one to you. You're going to take a derivative just like you would normally in all of the other problems that I've done. What is the derivative of a squared with respect to time? dA dt. Okay. What is the derivative of b squared with respect to time? You got it, Laura. What's the derivative of 1681? Nothing. Okay. Now, look here. I have 1, 2, 3, 4 unknowns. Well, I really don't have 4 unknowns because they've given us a moment in time. If we go back to the story, I'll show you where that moment is. So think about taking a picture at exactly when it's 9 feet above the ground. You go click. That's what you're doing at this moment in time. Okay. So let's go through this again, just so you can see what I go. The top of the ladder is sliding down. What's that? If I'm sliding down the top of the ladder. But what is that in relationship to these guys? Is it an A, a dA dt, a B if I'm sliding down? It's dA dt. That's what I'm actually going to figure out. Okay, how fast is the top sliding? While the bottom of it slides away from the wall at 4 feet per second. What's that? How fast is it, the bottom sliding out? That is the dB dt. 4 feet per second.
Why wouldn't it be D?
Because it says while the bottom of it slides away. It's not an actual length, okay? It's a feet per second, meaning that's a time thing. All right, how fast is the top sliding, dA dt, when it's 9 feet above the ground? So here's with the ladder problems. You actually have to draw another ladder at a moment in time, meaning the ladder is still 41, agreed? But when it's 9 feet above, meaning when my A is now 9, correct? I could actually figure out what B is using Pythagorean theorem. I could do 9 squared plus B squared equals 41 squared. This is an actual famous Pythagorean triple if you don't know. It's a 9, 40, 41. You can double check if you want to, but B is 40. At this moment in time, A is 9 and B is 40. Okay? So using all this information from here, plug this into 3 and let's see what we get. We would have 2 times, at the moment in time, A is 9. dA dt, have no idea. We're going to figure that out. How fast is it sliding? 2 times B at the moment in time is 40. And dB dt is 4. I can't remember who said it, Gray. I think it was you. It was negative. You knew it was going to be negative because it's sliding down. Very good. Notice I'm getting a negative answer. Was it gray?
Yeah.
You don't remember
I
saying?
said it, but I did not, I was not thinking. Yeah, I was not thinking about it.
Anybody know what negative 320 divided by 18 is?
It's 4, no, I'm sorry.
Negative 7.
0.78?
Yeah.
Okay. And that is feet per second. And again, that's why it's negative, because you are sliding down the wall. So the rate at which it's sliding down the wall is about negative 17 feet. That's the only reason it's a negative. So with ladder problems, you will have to do an extra Pythagorean at the end, like right before you plug in your stuff. So FYI. All right. Last and final two, you've been very good. I'm sorry that it's long, but we don't have anything else after this. Now for cones. And this is our last thing. I know, we got two different cones because they're both different. And good old Brian missed today's lesson.
Right.
Right.
Ay, ay, ay.
Wow.
Rain.
Okay, gravel is being dumped from a conveyor belt at a rate of 100 feet cubed per minute, forming a conical pile whose base diameter is 2 times the altitude. How fast is the height changing when the pile is 12 feet high? So something extra with cones here, just so you know. You've got this cone shape here of gravel being dumped. Okay, ooh, that looks terrible. For those who don't know, the formula for a volume of a cone is 1/3 pi r squared h. Here's our problem. We have way too many variables and not enough information. With cones, you want to make everything into r's or h's, meaning, and it's usually whatever they give you, it's usually h. It says how fast is the height. See how it's height? So we're actually, back here to my diagram, we're going to change the radius into be terms of h. I'll say that again. We're going to make our radius in terms of h. So let me read this again to you. Gravel is being dumped from the conveyor belt, from a conical pile, whose base diameter is 2 times the altitude, or 2 times the height. So if this base diameter would be 2 of these, agreed? Normally we'd call it R and R. What if I called it H and H? And then this was 2 of the H's. Would that make sense? My base diameter is equivalent to the 2 H's. Why is this helpful? Because back in this equation, instead of putting an r squared, what is my actual radius in terms of h's? I'm going to put h squared. My r is equal to h.
What's the diameter?
That is the diameter. Going across a circle is a diameter.
I thought the equation's radius.
Right. Your radius of this circle, of the base, is the diameter, right, is 2 r's, which is equivalent to 2 h's. All right. We'll figure out in a minute. So what is this actually? H what?
dH over dt.
H cubed. Now take the derivative of this formula. So this would be dv dt. What would this guy be? 1/3 pi h cubed. I'll wait. Pi h squared. What do I need to attach? dh dt. Okay. So now I'm going to go back to my story and try to find these 3 missing variables. Actually, there'll be 2 of them, and I'll have the other one to be finding. So gravel is being dumped from the conveyor belt at a rate of 100 feet cubed per minute. Is that dv dt, an h, or dh dt? Because the clue is 100 feet cubed, y'all. Whose base diameter is 2 times the altitude. We already dealt with that. How fast is the height changing? What's that? How fast is the height? That is derivative of height. dH dt, that's what I'm going to figure out. How fast is the height changing when the pile is 12 feet high? H is 12. Plug those in. dV dt is 100. pi stays pi. H is now 12 squared, and dH dt is what I figure out. So I'm going to divide by 144 pi, really. And again, when you divide, put a parenthesis around it. Anyone? 0.22 feet per minute. That's how fast the height of the gravel is changing when the height reaches 12 feet. Okay, so extra thing to do with cones. I'm sorry to tell you. We're gonna do one more cones like that, an extra thing to do, and then you're done. Give you a little sheet. You've been very good. That's why it's a double period. A conical tank with a radius of 6. Radius is 6. Height of 24 is leaking water. The water level is decreasing at a rate of 30.4 centimeters per minute. What is the rate of change of volume when the height is 9? Okay. Conical tank. Yes, that's what we want. A tank. It should be upside down. Probably I should have drawn it upside down, but whatever. Okay. Here's my problem again. You have numbers here, and we need a formula. And that formula needs to contain R's and H's, but actually it needs to contain either all R's or all H's. And in this case, since we're talking about height, I want everything in terms of H. So how is the radius and the height related to each other right now? 4R is equal to H, or R is equal to 1/4 of H. Would you agree to that? Okay. Did you all see that? If I take my R and I multiply by 4, wouldn't I have my H? Okay. So going back to my little formula here, you never, ever, ever take the derivative of an R and an H next to each other, ever. There's no you don't do product rule in this for that. So I first have to get all the R's to be H's. So R, we just have it over here, is 1/4 H. So right here, I'm going to replace R with 1/4 H squared. So 1/4 squared, for those who don't know, is 1/16. Then I have an H squared. Then I have an H, a pi, and a 1/3. Do you know what 1/3 times 1/16 is? 1/48. Put your pi, and then H squared times H is H to the what power? Okay, now you have a very good formula to take a derivative of. Okay, what's the derivative of V? dV dt. What's the derivative of 1/48 pi H cubed? It is 1/16. Very good. 1/16 pi. H is now squared, and then I include. Okay. You go back up here and tell me, you plug in what should be plugged in. Go back to the story and tell me what's what.
This is nuts. H is 9.
H is 9. Good job. We got that one.
dV dt is
dV dt is what?
No, it's not. DH over DT is 30.4.
Okay, why is that the dH dt?
Decreasing in height.
What? Yes, first of all, if you look right here, what is the rate of change of volume? That's what you're looking for. You're looking for dV dt. What is the rate of change of volume? The conical tank, the water level, or the water height, level is another word for height, is decreasing. Here's the only thing you're going to get wrong here. Do you see this word decreasing? You actually have to put a negative 30.4 right there. They didn't do it for you. All right, so plug all that in. And while you do that, I'm going to pass out your worksheet. If you get in the 400s as your answer, you are good.
Where's your calculator?
Negative.
It is negative because the water is leaking, so it's gonna.
Yeah, one on the
Just text Brian and just say, wow, like 1,400 don't get it.
This isn't much more violent. Oh, I got it wrong, and I don't know. I'm not doing it anymore.
You got it wrong.
Oh, I put the pie on the bottom. Yep, yep. Sorry, I didn't do it.
30 minutes. No way Brian's watching this. There's just no way.
Oh, Dylan, you need to put it in.
Tommy, there's no way they're gonna watch it. Jimmy, no
You need
way.
to put it in TikTok.
Yeah, put it in TikTok.
TikTok form, I gotta go in 8 seconds is what you're telling me?
I got this. So.
Kidding me.